systems that provide features enabling a process to contain multiple threads of control. These are the subtopics for Chapter 4. In this chapter, we will discuss concepts associated with multi-threaded computer systems, including discussion of the APIs. We will deal with a number of issues related to multi-threaded programming and its effects on the design of operating systems. Lastly, on the latter part, we'll explore on how the Windows and Linux operating systems support threads at the kernel level. A thread is a basic unit of CPU utilization. As defined in our previous topic, Chapter 3, we say that a thread is a lightweight process. Most software applications that run on modern computers are multi-threaded. An application typically is implemented as a separate process with several threads of control. Like a web browser might have one thread display images or text while another thread retrieves data from the network. In an email application program, it might have a thread for displaying the icons, okay, or update the display, another thread for responding keystrokes, another thread for fetching your uploads, and another thread for performing spelling and grammar. Many application programs can perform several CPU-intensive tasks in parallel across multiple computing cores. Several threads operate in the kernel, and each thread performs a specific task such as managing devices, managing memory, interrupts, and probably both interrupt handling and system calls. We have the structure of a multi-threaded server architecture. When the server receives a request from a client, it creates a separate process to service that request. In fact, this process creation method was very common before the concept of thread. Process creation is time-consuming and resource-intensive. If the new process will perform the same task as the existing process, why then incur all that overhead? It is generally more efficient to use the process that contains multiple threads. If the web server process is multi-threaded, the server will create a separate thread that listens for client requests. When a request is made, rather than creating a new process, the server creates a new thread to service the request and resume listening for additional requests. We have the benefits of multi-threading or multi-threading. These are broken into 4 categories, and that we have responsiveness, resource sharing, economy, and scalability. By responsiveness, multi-threading is considered as an active or interactive application. It may allow a program to continue running even if part of it is blocked or is performing a lengthy operation, thereby increasing responsiveness to the user. The quality is especially useful in designing user interfaces. For instance, consider what happens when a user clicks a button that results in the performance of a time-consuming operation. A single-threaded application could be unresponsive for the user until the operation had completed. In contrast, if the time-consuming operation is performed in a separate thread, then the application remains responsive to the user. On the concept resource sharing. So we regard process to be sharing resources through several techniques. So techniques could be through shared memory and message passing. Such techniques must be explicitly arranged by the programmer. Threads share the memory and resources of the process to which they belong by default. The benefit of sharing code and data is that it allows an application to have several different threads of activity within the same address space. By economy, allocating memory and resources for process creation is costly. Because threads share the resources of the process to which they belong, it is more convenient to create the context-switch thread. So, it is significantly more time-consuming to create and manage process than threads. On the concept of scalability, well, the benefits of multi-threading can be even greater in multiprocessor architecture where threads may be running in parallel on different processing cores. A single threaded process can run on only one processor regardless of how many are available. Earlier in the history of computer design, in response to the need of more computing performance, single CPU systems evolved into multi-CPU systems. A more recent similar thread in the system is designed to place multiple computing cores on a single chip. Each core appears as a separate processor to the operating system. Still on parallelism. So, data parallelism focuses on distributing subsets of the same data across multiple computing cores and performing the same operation of each core. Task parallelism involves distributing not data but tasks associated to threads, and this is across multiple computing cores. Each thread is performing a unique operation. Different threads may be operating on the same data or they may be operating on different data. Data parallelism involves the distribution of data across multiple cores, and task parallelism on distribution of tasks across multiple cores. So in practice, however, few applications strictly follow either data or task parallelism. So in most instances, applications use hybrid of these two strategies. On a system with single core, ito yung nasa taas. There is single computing core. Concurrency merely means that the execution of the threads will be interleaved over time because the processing core is capable of executing only one thread at a time. So in this case, we have one thread at a time. Now, on a system with multiple cores, we have core 1, we have core 2, it considers functionality on concurrency. It means that the threads can run in parallel. It can run in parallel because the system can assign a separate thread to each core. Amdahl's law is a formula that identifies potential performance gains from additional computing cores to an application that has both serial or non-parallel and parallel components. If S is the portion of the application that must be performed serially on a system with n processing cores. So in here we have an example. We assume that we have an application that is 75% parallel and 25% serial. If we run this application on a system with 2 processing cores, we can get a speed up of 1.6 times. If we add 2 additional cores to a total of 4, then the speed up is 2.28 times. One interesting fact about Amdahl's law is that as n approaches infinity, the speed up converges to 1 over S. For example, if 40% of an application is performed serially, the maximum speed up is 2.5 times, regardless of the number of processing cores we add. This is the fundamental principle on Amdahl's law. The serial portion of an application can have disproportionate effects on the performance we gain by additional computing cores. Some argue that Amdahl's law does not take into account the hardware performance enhancement used in the design of contemporary multiple core systems. Such arguments suggest that Amdahl's law may cease to be applicable as the number of processing cores continues to increase on modern computers. Support for threads may be provided either at a user level for user threads or by the kernel for kernel threads. User threads are supported above the kernel and are managed without kernel support, whereas the kernel threads are supported and managed directly by the operating system. Virtually all contemporary operating systems, including Windows, Linux, Mac OS, and Solaris, support kernel threads. In due course, a relationship must exist between user threads and kernel threads. We have the multi-threading models. Let's have first the many-to-one model. The many-to-one model to maps many user level threads to one. Ito, many user threads to one kernel thread. The thread management is done by the thread library in user space, so it is efficient. However, the entire process will block if a thread makes a blocking call, and that because only one thread can access the kernel at a time. Multiple threads are unable to run parallel on multi-core systems. However, very few systems continue to use the model because of its inability to take advantage of multiple processing cores. I skip. We have one-to-one model. Ito. One-to-one model. One-to-one model maps each user thread to a kernel thread. It provides more concurrency than many-to-one model by allowing another thread to run when a thread makes a blocking system call. It also allows multiple threads to run in parallel on multiprocessors. Kaya lang, the only drawback to this model is that creating user thread requires creating the corresponding kernel thread. So, to, simultaneous. Pag nag-create si user thread, nandun din ang pag-create kay kernel thread. The overhead of creating kernel threads can be burdened by the performance of an application. Most implementations of this model restrict the number of threads supported by the system. Linux, along with the family of Windows operating systems, implement one-to-one model. We have many-to-many model. This model multiplexes many user-level threads to a smaller or equal number of kernel threads. The number of kernel threads may be specific to either a particular application on a particular machine. Such an application may be allocated more kernel threads on multiprocessor than a single thread. The many model makes use of multiplexers. Okay. On variation on the many-to-many model, still multiplexes many user level threads to a smaller or equal number of kernel threads, but also allows a user level thread to be found to a kernel thread. So this variation is seen in this figure. The Solaris operating system supported the two-level model in versions older than Solaris 9. However, beginning with Solaris 9, the system uses the one-to-one model. On the concept of thread libraries, this library provides the programmer with an API for creating and managing threads. There are two primary ways of implementing a thread library. The first approach is to provide a library entirely for the user space with no kernel support. All the code and data structures for the library exist in user space. This means that invoking a function in the library results in a local function call in user space and not a system call. The second approach is to implement a kernel library supported directly by the operating system. In this case, code and data structures for the library exist in the kernel space. Invoking a function in the API for the library typically results into a system call to the kernel. We have the pthreads. Pthreads refer to the POSIX standard of IEEE 1003.1c, and that is defining an API for thread creation and synchronization. This is a specification for thread behavior and not an implementation. Operating system designers may be implementing the specification in any way as they wish. Numerous operating systems implement the pthread specification. Most are Unix type systems, including their versions on Linux, and then it's also implemented in Mac OS X and Solaris. Although Windows doesn't support the pthreads natively, some third-party implementations for Windows are available. The C program shown in this figure demonstrates the basic pthreads API for constructing a multi-threaded program that calculates the summation of a non-negative integer in a separate thread. The programs begin in main. After some initialization, it creates a second thread that begins control in the runner function. All pthreads program must include pthread.h in the header file. The illustration shows that you can join on 10 threads using the pthread by defining the num threads value here. The main thread and the summation thread share the object instance of the sum. We have the class sum here. The shared object is referenced through the appropriate getSum and the setSum methods. We have the setSum methods. The parent threads in pthreads and Windows libraries use pthread join and wait for single object to wait for the summation threads to finish before proceeding. One way to address difficulties and better support the design of multi-threaded application is to transfer the creation and management of threading from application developers to compilers and runtime libraries. There is a strategy termed implicit threading. This is a popular trend today. In this section, we will explore 3 alternative approaches for designing multi-threaded programs that can take advantage of multi-core processors through implicit threading. There are 3 methods to be explored: thread pools, OpenMP, Grand Central Dispatch. Whenever the server receives a request, it creates a separate thread to service the request. Creating a separate thread is certainly superior to creating a separate process, and a multi-threaded server nonetheless has potential problems. Una, the issue on the amount of time required to create the thread together with the fact that the thread will be discarded once it has completed its work. Then, the second issue is more troublesome. Say, if we allow all concurrent requests to be serviced in the new thread, we have not placed a bound on the number of threads concurrently active in the system. Unlimited threads could exhaust system's resources such as CPU time and that also the memory. One solution to this problem is to use a thread pool. The general idea behind a thread pool is to create a number of threads at process startup and place them into a pool where they sit and wait for work. OpenMP is a set of compiler directives as well as an application program interface for programs written in C, C++, or Fortran that provide support for parallel programming in shared memory environments. OpenMP identifies parallel regions as blocks of code that may run in parallel. The application programmers insert compiler directives into their code at parallel regions, and these directives instruct the OpenMP runtime library to execute the region in parallel. So we have here the C program that illustrates a compiler directive above the parallel region containing a printf function. So we have here the printf statement. Now, in this code, we have include omp.h, which means for OpenMP. So, on the Pragma OMP parallel, it creates as many threads are there on processing cores of the system. Thus, for a dual core system, 2 threads are created. Say kung quad core, syempre there are 4 threads created. All the threads then simultaneously execute the parallel region. As each thread exits the parallel region, it is terminated. OpenMP provides additional directives for running code regions in parallel, including the parallelizing of loops. In addition to providing directives for parallelization, OpenMP allows developers to choose among several levels of parallelism. For example, they can set the number of threads manually. It also allows developers to identify whether data are shared between threads or may be private to a thread. OpenMP is available on several open source and commercial compilers for Linux, Windows, and Mac OS X systems. The Grand Central Dispatch, or the GCD. This is a technology for Apple's Mac OS X and iOS operating systems. This is a combination of extensions to the C language, an API, and a runtime library that allows application developers to identify sections of code to run in parallel. Like the previous OpenMP concept, GCD manages most of the details of threading. GCD identifies extensions to the C and C++ languages known as blocks. So a block is a simply self-contained unit of work. It is specified by a caret symbol. Ito. It is inserted in front of a pair of braces. Ganyan paggamit. A simple example of the block is shown. Halimbawa, it will be integrated on the printf function. So this is the format. GCD schedules blocks for runtime execution by placing them on dispatch queue. When it removes a block from a queue, it assigns the block to an available thread from the thread pool it manages. GCD identifies 2 types of dispatch queue. Ito. Blocks placed on a serial queue are removed in first in, first out order. Once a block has been removed from the queue, it must be completely executed before another block is removed. Each process has its own serial queue known as the main queue. Developers can create additional serial queues that are local to a particular process or probably processes. Serial queues are useful for ensuring the sequential execution of several tasks. Blocks placed on a current or concurrent queue are also removed in, first out order. But several blocks may be removed at a time, thus allowing multiple blocks to execute in parallel. There are three system-wide concurrent dispatch queues, and they are distinguished according to priority. So we have low, default, and high. Priorities represent approximation of the relative importance of blocks. Blocks with a higher priority should be placed in high priority dispatch queue. The fork system call is used to create a separate duplicate process. The semantics of the fork and exec system calls change in a multi-threaded program. Some Unix systems have chosen to have two versions of fork, one that duplicates all threads and another that duplicates only the thread that invokes the fork system call. A signal may be received either synchronous or asynchronous, depending on the source of and the reason for the event being signaled. Every signal has a default signal handler that the kernel runs when handling that signal. This default action can be overwritten by a user-defined signal handler that is called to handle the signal. A signal may be handled by one of the two possible handlers. We have the default signal handler and the user-defined signal handler. Every signal has a default signal handler that the kernel runs when handling that signal. This default action can be overwritten or overridden by a user-defined signal that is called to handle the signal. Signals are handled on different ways. Some signals, such as changing the size of a window, are simply ignored. Others, like an access to an illegal memory, are handled by the terminating program. Handling signals in single-threaded programs is straightforward. Signals are always delivered to a process. However, delivering signals is more complicated in multi-threaded programs, where a process may have several threads. In general, there are four options in handling the signal. First, deliver the signal to the thread to which the signal applies. Second, deliver the signal to every thread in the process. Deliver the signal to certain threads in the process, or assign a specific thread to receive all signals for the process. The table here illustrates pthreads that allows threads to disable or enable cancellation. Obviously, a thread cannot be cancelled if cancellation is disabled. However, cancellation requests remain pending, so the thread can later enable cancellation and respond to the request. The default cancellation type is deferred cancellation. This occurs when a thread reaches a cancellation point. One technique for establishing a cancellation point is to invoke the pthread test cancel. If a cancellation request is found to be pending, a function known as a cleanup handler is invoked. This function allows any resources that the thread may have acquired to be released before the thread is terminated. A thread is to be cancelled is referred to as target thread. A thread that is to be cancelled is often referred to as the target thread. Okay? Yung cancellation of a target thread may occur in two different scenarios. Maaring there is an asynchronous cancellation and that one thread immediately terminates the target thread. Meron ding deferred cancellation. The target thread checks whether it should terminate, allowing it with the chance to terminate itself in an orderly fashion. The difficulty with cancellation occurs in situations where resources have been allocated to a cancelled thread or where a thread is cancelled while in the midst of updating data and it is sharing the resources of other threads. This becomes especially troublesome with asynchronous cancellation. Often, the operating system will reclaim system's resources from cancelled thread but will not reclaim all resources. Therefore, canceling a thread asynchronously may not be free from unnecessary system-wide resource. With deferred cancellation, in contrast, one thread indicates that a target thread is to be cancelled, but cancellation occurs only after the target thread has checked a flag to determine whether or not it should be cancelled. The thread can perform this check at a point at which it can be cancelled safely. Threads belonging to a process share the data of the process. Indeed, this data sharing provides one of the benefits of multi-threaded programming. However, in some circumstances, each thread might need its own copy of certain data. Now, we will call such data as thread local storage, or the TLS. So, for example, in a transaction processing system, we might service each transaction in a separate thread. Each transaction might be assigned a unique identifier. So to associate each thread with its unique identifier, we use thread local storage. Local variables are visible only during a single function invocation, whereas TLS data are visible across function invocations. In some ways, TLS is similar to static data. The difference is that TLS, or the thread local storage, data are unique to each thread. Most thread libraries, including Windows and pthreads, provide some form of support to thread local storage. Kernel provides an application with a set of virtual processors or lightweight process, and the application can schedule user threads onto an available virtual processor. Further, the kernel must inform an application about certain events. This procedure is known as app call. App calls are handled by the thread library. App call handlers must run on a virtual processor on an event that triggers. An app call occurs when an application thread is about to block. So the kernel makes an app call to the application, informing it that a thread is about to block and identifying a specific thread. Windows implements the Windows API, which is the primary API for the family of Microsoft operating systems like Windows 98, NT 2000, XP, as well as Windows 7. Much of what is mentioned in this section applies to the entirely family of operating systems. A Windows application runs as a separate process, and each process may contain one or more threads. The Windows API for creating threads is covered in each user-level threads that maps to an associated kernel thread. The general components of a thread include a thread ID that uniquely identifies the thread, a register set representing the status of the processor, a user track employed when the thread is running in user mode, and a kernel stack employed when the thread is running in a kernel mode. A private storage area is used by various runtime libraries and dynamic link libraries, or known as the DLLs. The registers set stacks in private storage area are known as the context of the thread. Now, there are primary data structures to be considered in the thread. The E thread, or the executive thread block, K thread, the kernel thread block, and the TEB for thread environment block. Okay, isa-isahin natin. The key concepts of the E thread include a pointer to the process to which the thread belongs and the address of the routine in which the thread starts control. The E thread also contains a pointer to the corresponding K thread. Okay, tapos pupunta na siya dito. The K thread includes scheduling and synchronization information for the thread. In addition, the K thread includes the kernel stack that is used when the thread is running in the kernel mode, and a pointer to the next, that is TEB. The E thread and the K thread, to emphasize, exist entirely in the kernel space. This means that only the kernel can access them. Then we have the TEB, or the thread environment block. This is a user space data structure that is accessed when the thread is running in user mode. Among other fields, the TEB contains the thread identifier, a user mode stack, and an array for thread local storage. This figure describes the structure of a Windows thread. The primary data structures of a thread include EThread for executive thread block, the K thread, the kernel thread block, and the TEB for the thread environment block. Unahin natin si EThread. The key components of the EThread include a pointer to the process to which the thread belongs and the address of the routine in which the thread starts to control. The EThread contains a pointer to the corresponding K thread. The K thread includes scheduling and synchronization information for the thread. In addition, the K thread includes the kernel stack used when the thread is running in the kernel mode, and a pointer to the TEB. TEB contains the thread identifier, a user mode stack, and an array for a thread local storage. Linux provides the fork system call with the traditional functionality of duplicating a process. Linux also provides the ability to create threads using the clone system call. However, Linux does not distinguish between processes and threads. In fact, Linux uses the term task rather than process or thread when referring to a flow of control within a program. Suppose that clone system call is passed to the flags clone fs, clone vm, clone signhand, and clone files. So then the parent and child task will then share the same file system information, such as the current working directory, the same memory space, the same signal handlers, and the same set of open files. Using clone system call in this fashion is equivalent to creating a thread, since the parent task shares most of its resources with its child task. However, if none of these flags is set when clone is invoked, no sharing takes place, resulting in functionality similar to that provided by the fork system call. The varying level of sharing is possible because of the way a task is represented in Linux kernel. A unique kernel data structure, specifically the struct task struct, exists for each task in the system. The data structure, instead of storing data for the task, contains pointers to the other data structures where the data are stored. For example, data structures that represent the list of open files, signal handling information, and virtual memory. When fork is invoked, a new task is created along with a copy of all the associated data structures of the parent process. Linux provides the fork system call with the traditional functionality of duplicating a process. Let us now summarize Chapter 4 on topic thread. So, pinanggalingan po natin is Chapter 3, process, then process. Now, we have thread. A thread is a flow of control within a program. Tapos, in this chapter, pinag-usapan po natin si multithreaded. A multithreaded process contains several different flows of control within the same space address or the same address space. The benefits of multithreading include increased responsiveness to the user, resource sharing within the process, economy and scalability factors such as more efficient use of multiple processing cores. User-level threads are threads that are visible to the programmer and are unknown to the kernel. The operating system kernel supports and manages kernel threads. In general, user-level threads are faster to create and manage than a kernel threads because no intervention from the kernel is required. There are three different types of models, and that it relates the user and the kernel threads. The many-to-one model maps many user threads to a single kernel thread. The one-to-one model maps each user thread to a corresponding kernel thread. The many-to-many model multiplexes many user threads to smaller or equal number of kernel threads. Most modern computer or operating systems provide kernel support for threads. These include Windows, Mac OS X, Linux, and Solaris. The thread libraries provide the application programmer with an API for creating and managing threads. Three thread libraries are in common use, like POSIX threads, Windows threads, and Java threads. In addition to explicitly creating threads using the API provided by a library, we can use implicit threading, in which the creation and management of threading is transferred to compilers and runtime libraries. Strategies for implicit threading include thread pools, yung OpenMP, yung GCD, or Grand Central Dispatch. Multi-threaded programs introduce many challenges for programmers, including the semantics of the fork and the exit system calls. Other issues, including signal handling, thread cancellation, the thread local storage, and schedule activations, were discussed. People, please take time to comprehend this discussion, as asynchronous activity is now provided for everyone for this week's submission. Please be ready for the validation of your submissions as well as the discussions for Chapter 4. Thank you very much, everyone. Keep safe.